All right, welcome everyone. Today we're going on a bit of a digital archaeological dig. We're getting right into the absolute oldest, most fundamental code of Bitcoin. We're going to uncover a seriously cool piece of hidden history and see how a tech enigma from over a decade ago is literally just now being solved.
Okay, let's dive into this, because it's honestly one of the greatest mysteries in crypto history. Why on earth did the architect of a revolutionary electronic cash system spend time hard-coding a virtual poker game into the very first alpha release? Like, was this just some side hobby, or was it the foundation of a much, much bigger plan?
To show you this isn't just some wild internet rumor, look at this. Buried deep in the original 2008 Bitcoin source code, there are literally hundreds of lines defining a graphical user interface for a poker game. We're talking functions like deal, fold, raise, and get this, they were added months before the famous Bitcoin white paper was even published.
So here's our roadmap for today. We'll unpack the mystery in version 0.1.0, look at the UGIGA law and the historical motivations, tackle the infamous mental poker problem, explore the modern card table protocol solution, and finally do a deep architectural comparison.
Starting right off with Section 1, the mystery in V0.1.0. Looking back at this unfinished vision, it's totally clear Bitcoin was never meant to be just a simple financial tool. It was originally envisioned as an entire decentralized network framework.
Right alongside the financial ledger, Satoshi actually packed in an IRC chat client so nodes could find each other without central servers, a peer-to-peer eBay-style marketplace, and yeah, the poker framework. It absolutely shows an early intent to create a completely disintermediated digital economy. But as you can imagine, cramming all of that into one single monolithic application really overburdened the system early on, which is why it was eventually removed.
Moving to Section 2, UIGEA and historical motivation. Now, what's really interesting about this is the timing. Why prioritize a poker game inside a currency app? Well, it all comes down to the intense regulatory pressure of the mid-2000s acting as a massive catalyst. This timeline right here tells the whole story. Back in 2006, the US passed the UIGEA law, basically making it illegal for banks to process transactions for online gaming operators. The industry's liquidity just collapsed overnight, and right when this massive, centralized financial blockade happens, that is exactly when Satoshi starts coding this decentralized poker framework. The ultimate workaround to that kind of censorship was replacing those vulnerable trusted third parties, like banks, with pure cryptographic proof. A decentralized ledger was literally the perfect technical solution to bypass financial blacklists in industries like online gaming.
But entering Section 3, we hit a massive cryptographic paradox. This was the giant technical hurdle that stopped Satoshi's original poker code dead in its tracks. If you're not familiar, mental poker is basically the mathematical nightmare of trying to play a provably fair game of cards over a network without relying on a central server or a trusted dealer. It's kind of like trying to play a high-stakes game of Texas Hold'em over the phone with someone you completely distrust, where nobody can cheat and there's no dealer to shuffle the deck.
And here's the fundamental paradox Satoshi ran into. A blockchain, by its very design, is a transparent public ledger. If you try to run a deck of cards through it, everyone can see everyone else's hand. The original codebase simply lacked the advanced cryptography needed to hide whole cards. Processing them in local RAM would have exposed everything, so the project essentially hit a brick wall.
All right, Section 4, the card table protocol solution. Fast forward to today, and we actually have a modern resolution to this decade-old problem. A developer going by the pseudonym Prof. Faustus built the card table protocol on the BSV network to finally execute that original blueprint.
Card table completely modernizes the architecture. It's totally dealerless, non-custodial, and operates entirely within the blockchain, meaning absolutely zero database servers. Instead of traditional backends, it translates every single game event into a signed transaction, using the network's native UTXOs as a state machine to track the game. The very first game they implemented? A classic called In Between, or Acey-Deucey. And this formula brilliantly illustrates how they avoid the network bottlenecks of the past. Instead of broadcasting every tiny move, like a fold or a raise, to the entire network, players cooperatively and privately sign off-chain state transitions between themselves. Then, they only settle the final, decisive transaction on the public ledger. Now, you might be wondering what happens if someone is losing and just unplugs their computer to hold the game hostage. Well, the protocol solves this using a clever waiting period mechanism tied to the network's built-in timers. If a player goes dark, the smart contract essentially calls a timeout, guaranteeing that honest players automatically get their funds back. It's totally foolproof.
So how do they actually hide the digital cards? Think of it like this. It's like putting a padlock on a box, passing it to a friend who adds their own padlock, and then removing them one by one. By using commutative encryption, they turn the hidden cards into encrypted digital assets. These are finally validated on-chain without ever prematurely revealing anyone's hand.
Bringing us to our final section, architectural and comparative analysis. Let's do a side-by-side technical teardown of that primitive 2009 codebase versus the modern protocol we have today.
So the crucial point here is the evolution of the software. The 2009 framework was just this monolithic block of C++ that didn't even have the logic to enforce poker rules. But Cardtable, it's completely modular. Because Turing-complete opcodes were restored in BSV, Cardtable can actually enforce the complex rules of the game directly on the ledger, making it incredibly secure.
The absolute biggest leap in software engineering here is the decoupling of tasks. In the old v0.10 design, if your poker GUI crashed, it literally risked taking down your entire consensus validator node. No way that scales, right? Today, Cardtable uses decoupled SPV, simplified payment verification. The client handles all the heavy game state computation locally, and the network is strictly used to seal the final transaction. It is infinitely more scalable.
Which brings us to our final provocative thought. Unearthing this old code isn't just some neat piece of trivia. It's a window into the absolute original intent of this technology. By finally solving the mental poker problem with tools like Cardtable, have we actually unlocked the original 2008 blueprint for a completely disintermediated, trustless digital economy? It's a fascinating question to chew on. Thanks so much for joining me on this explainer, and I highly encourage you to go dig into this source code for yourselves.